All right, special permutations. I'm going to be solving this with Bitmasking and DP. I'm going to show you how I do it, man. You're given a zero-indexed integer array nums containing n distinct positive integers. A permutation of nums is called special if for all indices for 0 less than equal to I less than equal to n minus 1, either nums I mod nums I plus 1 is 0, or nums I plus 1 mod nums I is 0. Return the total number of special permutations. As the answer could be large, return it mod 1,000,000,007. And so first thing I like to do, I always like to make n equal to the number of elements in nums, just like that. And then since we're using bit masks and stuff, I like to find the value that will represent when all the bits in the mask are set. So I'm gonna say all set is equal to, we shift 1 n and then we minus 1, and that's like 2 to the power of n minus 1 basically. And I'm gonna be using top-down DP to solve this because I don't know how to do bottom-up. That stuff is too hard. So I like to use lambdas here. I'm gonna say DP, lambda DP function, and you gotta pass the actual DP function to itself. And we'll need to know the previous number that we selected. We will also need the mask that we got. And so I'm gonna say previous I. I guess our base case you can say is like if the mask is all set. So if mask is equal to all set, that means we have selected every single number in nums. So we can say that this is a valid permutation of nums, and we should just return 1 to start that count. So in this recursive function, I guess what we need to do is we need to iterate through all of the numbers in nums, like so. And then we gotta check, like, have we used this number before? So how do we do that? That information is in the mask. So we can just check the bit at the ith index in the bit mask to see if that bit is set or not. Basically if it's a 0 or a 1. And we can use like bitwise operations to do that. Like, so if the mask and the bit that we're at, or this should be I, if this is not set, that means we have not used the number, and we should probably see if we can use it. How do we know we can use this number? Well, if the previous index that we selected and the current index that we're at, if we can mod them together or switch it around and it's equal to 0, then we can select that number. But initially, I'll call this DP function with previous I set to -1. So I'm just gonna add in a little extra if statement here. So like if previous I is equal to -1, that means we can always select that number. Otherwise, we should probably check if the mod thing works. So I'll fill this part in a bit. So what are we doing? We're checking if the previous index and the current index modded together will give us 0. So if nums I mod with nums previous I is equal to 0, or if nums previous I mod with nums I equal to 0, then we can select this number. How do we select the number? Well, first we have to put in the mask that we selected this number, and it's like similar to this thing right here where we're checking if we've seen it. Actually, wait, let me say we gotta keep track of like how many ways we successfully generated permutations here, and we'll do that in this variable called ret. So ret equal ret plus DP the mask. So we have to modify this mask to say that we've selected this new number, and we do that by, we use the bitwise OR operator, and then we do the shift with the I, just like that. So that's gonna set that current index that we're at in the mask to be a 1, which means that we've already processed this number and we shouldn't do it again. And then we send the previous I, which is just I right now. All right, and then I guess up here where it's like if previous I is -1, that means we have not selected a previous number yet. This is probably the first time the iteration is going on or the recursion is happening. So we can just select it. And then we can just return this ret, but this is supposed to be a DP problem. We still haven't introduced the cache here yet, so I'm just gonna do that right now. I like to represent the cache usually as a 2D vector when I can. Sometimes I gotta use like an unordered map. But anyways, this is my cache and we need it to be the size of all set. I'm gonna add +1 just so I don't have any weird out of range errors or something. And then we also need the second vector to be of size n. I'm gonna also add +1 there. Maybe +2 for super good luck because I am sending a -1 here and I need to pad that previous I so it doesn't cause any weird errors. I'm gonna set all the values in the cache to -1 and -1 will mean that we have not seen this result yet. So here we can check the cache. Like if we've seen these states in the cache, and I'm gonna add 1 here to the previous I because I'm sending a -1 initially and I just need to pad that because we can't access -1 in the thing. That's like not that great. So if it's not equal to that, then we just return that. And then we need to set the values in the cache at the end here when we return. And the problem statement says the number may be very large and we should mod it with a number there. So I'm gonna create that mod up here. And it's 1E9 + 7, which is like a really big prime number. That's like 1,000,000,007. And I'm just gonna mod the things over here. This is like pretty standard stuff in some DP problems on LeetCode. You'll see it in so many things. So I'm gonna do that to mod those things, and that line is looking really long, but it's all good. And then that's it, man. I think that's it. Hopefully it will work when I press submit. Actually, I have to call it first. So return DP. The mask is, we're gonna start off the mask with 0. That means none of the bits are set in the mask. So none of the indices are seen yet. And then I said I'll send in a -1 as the initial value for previous index when we haven't selected any previous. And that's what like this part is for. Like we don't have to check the mod thing because there's no other previous number to mod. Anyways, let's see if this passes in the first try, man. I hope so. Oh, look at that. First try. That's how I do that problem. Special permutations.